Welcome to Math Shorts, tantalizing mathematical tidbits that will amaze, entertain, and delight. Math Shorts is brought to you by the Ottawa Zone for Mathematics Education. The Ottawa Zone for Mathematics Education is a chapter of the Ontario Association for Mathematics Education. Information about both organizations can be found in the information for this video.
In this episode of Math Shorts, we're going to be looking at a peculiar property of primes. Since we're going to be talking about prime numbers, let's remind ourselves of what a prime number is. Here's the first 13 natural numbers listed along with their factors. Numbers such as 2, 3, 5, 7, 11, and 13 whose only factors are 1 and itself, in other words, they have two factors, are called prime numbers. These are like the building blocks of the whole numbers or the natural numbers. Numbers like 4, 6, 8, 9, 10, and 12 that have factors of 1 in themselves as well as something else are called composite numbers. Now, you might have noticed that I didn't talk about the number 1. 1 is a little bit different. It only has itself as a factor. And as a result, we call it a unit. That won't be necessary for what we're talking about, but in higher mathematics, treating this as a separate type of thing is really important. So, mathematicians for years have been searching for patterns in prime numbers. So let's take a look at some of the prime numbers. So in this list of the first couple hundred numbers, the prime numbers are highlighted. Now if you look at it, you'll notice that they're kind of scattered all over the place. We've got some places where there's a lot of them bunched together, and we've got other places where there's big gaps where there's hardly any prime numbers. Now, most of you should know that since 2 is a prime number, 2 goes into all of the even numbers. So every number, every prime bigger than 2 is an odd number. What we're going to look at today is we're going to see what happens when we bring 3 into the mix. So when we consider 2 and 3. So looking at both of these things together, I'm actually going to look at 2 times 3, which is 6, and all its multiples. So there in green, I've put all the multiples of 6. Now, it might be hard to spot what the heck's going on here because there's too many things in our field of view. But if we take out everything except for the primes and the multiples of 6, something happens. Other than 2 and 3, every prime number, it seems, is attached to or beside a multiple of 6. It's either 1 above a multiple of 6, like 7, or 1 below a multiple of 6, like 5. Now, if you look through the list, there might seem to be numbers like 79 and 157 that seem to be on their own. But if you look closely, 79 is at the beginning of the list. If I back up 1, 78 is a multiple of 6. So again, it's sort of attached to it. And the same thing over here, 157 and 156. So we're going to explore whether this pattern actually continues and try to determine, if it does, why that happens. To make this easier to see, let's arrange the numbers into a table with 6 columns. And this way, the 6th column is going to be our multiples of 6. The 5th column is going to be all the numbers that are 1 less than a multiple of 6. And the 1st column is going to be all the numbers that are 1 more than a multiple of 6. And when we have the numbers arranged this way, it's really easy to see that it seems that all of our prime numbers are either one more or one less than a multiple of 6. But why is this true? And will this pattern continue on forever and ever and ever? To give us an idea, let's focus in on one of the rows. So let's look at the numbers between 43 and 48. So 43 and 48, there's one of our rows. Now we're really concentrating on the multiples of 6, so let's throw in 42 as well so that we can see that 43 is one more than a multiple of 6 and 47 is one less than a multiple of 6. Now, all of these numbers between our multiples of 6 we can write in terms of the multiples of 6. So for instance, 42 we can write as 6 times 7. Well then 43 I can write as 6 times 7 plus 1. And 44 I can write as 6 times 7 plus 2. 45 would be 6 times 7 plus 3, 6 times 7 plus 4 for 46, and 6 times 7 plus 5 for 48. Now, on top of that, everything that's going to be in the same column as 43, that first column, is actually going to be 6 times something plus 1. The second column is going to be 6 times something plus 2, and so on down the line. Now we haven't forgotten about 48. 48 is 6 times 8. And we could have actually referenced these numbers 43 to 47 in terms of that multiple of 6 as well. We could have said 47 is 6 times 8 minus 1. And 46 is 6 times 8 minus 2. 45, 6 times 8 minus 3. 44 is 6 times 8 minus 4. And 43 is 6 times 8 minus 5. So let's consider these things in algebraic notation. So I'm going to write my first number as 6 times k for some integer k. My next number is 6k plus 1, 2, 3, 4, 5. And then I'm going to get another multiple of 6. Now if I wanted to, I could write this as actually 6 times bracket k plus 1. It'd be the next number up. But we'll leave it like that as now. And similarly, we could have written these numbers in terms of this 6L as 6L minus 1 down to 6L minus 5 as we've shown before. Now we're interested in what numbers are primes. Now we know primes have only themselves and 1 as factors. Looking at 6k, well, 6 is 2 times 3. So I can actually factor 6k as 2 times 3 times k. So I know 2 and 3 are factors of 6k as well as 1 and 6k. So that tells us that 6k can't be prime. And similarly, 6l can't be prime. Now I'm going to look through these other numbers with the same idea. Can I find a factor that isn't 1 or itself? Now if I look at 6k plus 2, 6 is even and 2 is even. So 2 goes into this whole number. I can write this as 2 times 3k plus 1. Even if I wrote this as 6k minus 4, 2 goes into 6 and 4. So I can write this as 2 times 3l minus 2, which means that 2 is going to be a factor of this type of number, no matter what, as well as 1 in itself. So that's not going to be prime. Similarly, 6k plus 4, 6l minus 2 are also even numbers. So 2 is going to go into those, and they're not going to be prime. Now, what about 6k plus 3? Well, 3 goes into 6. So, and 6k minus 3, same idea. So I can write each of these as 3 times something. So 3 is going to be a multiple of 6k plus 3 or 6k minus 3. So those aren't going to be prime. Now, all that I'm left with is 6k plus 1 and 6k minus 5. 6k plus 5 and 6k minus 1. I can't say whether these things have factors or not. In some cases they will, some cases they won't. But from the notation that we have, we don't know whether those are going to be prime or not. But we know for sure that these other ones are not going to be prime, which leads us to the following theorem. That all primes larger than 3 are either one more or one less than a multiple of 6. Now, that didn't say that if you go one more or one less than a multiple of 6, it's a prime. It says primes are going to fall into these categories. Now, we can write this in a little bit more mathy of a way by saying that if p greater than 3 is a prime, then p is going to be 6k plus 1 or 6k minus 1 for some natural number k greater than or equal to 1. Now, we can write this in another way as p is going to be 6k plus or minus 1. So we see that our theorem actually holds true for values bigger than 3. We get our primes are all in the first column or in the fifth column. No matter how far we go, and we could keep going with this list, and that's the only place that we'd find primes. Now, this idea of putting numbers into these tables, like we did here, is actually an idea called modular arithmetic that we'll talk about at some future Math Shorts video. And sort of arranging things this way, we would be considering things what we would call modulo 6, because we've got 6 columns. And then we'd really be considering the columns of numbers. And so everything in the first column is where the primes end up, or in the fifth column. So we'd say things that are congruent to 1 or 5 modulo 6. Now, when we originally looked at the prime numbers, this is our list from the beginning, I was being a little bit sneaky because I actually had arranged these numbers in a table with 13 columns, or modulo 13, and 13 is a prime. So what we did for 6, by picking 6, which is 2 times 3, we had a lot of numbers between 1 and 6, 2, 3, and 4, which shared factors with 6. When I pick 13, nothing shares a factor with 13 from 1 to 13 other than 1. And as a result, if I start looking for primes, there's primes in the first column, second, third, fourth, fifth, sixth, seventh, 8th, 9th, 10th, 11th, and 12th. And 13 is the only prime in this column. So I kind of set it up so that you wouldn't be able to see a pattern like this. Now, one of the consequences of our theorem is that if you look at any 6 consecutive numbers, whether that 6 consecutive numbers ends with a multiple of 6, or begins with a multiple of 6, or has a multiple of 6 somewhere in the middle, if you look at those stretches and we're bigger than 3, like the numbers inside are bigger than 3, then at most you're going to have 2 primes. One above and one below are multiple of 6. Now, that doesn't mean you're going to have 2 primes, because sometimes you're going to only have 1 prime, like here, here, and here. And in some cases, you're actually going to get no primes. But it doesn't matter whether you're going up to a multiple of 6 or from a multiple of 6, because if you pick 6 numbers in a row, one of them has to be a multiple of 6. Now, another consequence of our theorem is if you look at the beginning of our prime numbers, 3, 5, and 7 are 3 consecutive odd numbers that are all prime. Now, this is actually a group of 5 numbers, which is smaller than 6, and I get 3 primes. Our theorem says we had to start bigger than 3 because we were actually building things on 2 and 3, which gave us our 6. as a result of our theorem, this is the only place you're going to find 3 consecutive odd numbers being prime. There's lots of places where you get 2 consecutive odd numbers being prime, but then there's going to be a gap. And these things are called twin primes, and we might talk about that at some later date. Now, there's nothing that stops us from considering other groups of primes. Sort of a natural thing. We're used to working in base 10, which is 2 times 5, and 2 and 5 are both prime. We could have gone through the same analysis that we did for 6 for things with respect to multiples of 10. I can write all numbers as either a multiple of 10 or 1, 2, 3, 4, 5, 6, 7, 8, 9 above a multiple of 10, or 1, 2, 3, 4, 5, 6, 7, 8, 9 below a multiple of 10. And if we look, again, multiples of 10 are going to be multiples of 2 and 5, so they can't be prime. If I look, 2, 4, 6, 8, and 10 are all even numbers, so these numbers here are all going to be multiples of 2. They're going to be even, so they can't be prime. And this guy in the middle, 10k plus 5 and 10l minus 5, are both multiples of 5. So those things are not going to be prime. So the only things that could be prime are 10k plus 1, 10k plus 3, 10k plus 7, or 10k plus 9. Or in terms of the subtraction, 10l minus 9, 10l minus 7, 10l minus 3, or 10l minus 1. And if we want to get cute, we can write it as 10k plus or minus 1, 10k plus or minus 3. So same idea. That doesn't mean that those numbers are going to be primes. It just means that primes will only show up in the first, third, seventh, and ninth columns if I do columns of 10. And if I look here, other than the beginning where 2 and 5 show up, there's my first column with primes, my third column with primes, my seventh column with primes, and my ninth column with primes, and nowhere else other than the 2 and the 5 are there primes. Now, this sort of gives us a way to reduce the numbers that I have to check if I want to look for primes. So for instance, if I'm only looking at 2, I know that every even number is going to be composite, which means if I only look at the odd numbers, I've kind of cut down the numbers by 1/2. So if I wanted to find the primes up to 100, I know all the even numbers are not going to be prime, so I can throw them out, and I would only have to check the odd numbers. I cut my numbers in half. Similarly, if I only looked at 3 and I said, okay, I know that 3 is prime, so let's look at everything that's not a multiple of 3. Well, that would only reduce things by 33%. If I only looked at things in terms of 5s, I know that 5, 10, 15, 20, that would reduce things by 20%. But if I do combinations of things, we saw that if I look at 2 and 3 together, that means I'm going to be looking at multiples of 6, and when we looked at things of multiples of 6, I could eliminate 4 of the possibilities. So I only end up with 6k plus 1 or 6k minus 1, which means I've actually reduced 2/3 of the numbers that I want to check. But I could do that for any combination of primes. What if I look at 2s and 5s are multiples of 10s that we just looked at? I get those guys, but that's only a reduction of 60%. Because 3s are a little bit closer together than 5s, doing 2s and 3s together is going to give us more reduction than 2s and 5s. So similarly, if I look at 3s and 5s, it's going to be better than 3s or just 5s, but it's not going to be as good as 2s and 3s or 2s and 5s. To actually do better than our 6k plus or minus 1, we'd actually have to incorporate 2s and 3s and 5s together. and 2 times 3 is 6, times 5 is 30. And if I looked at multiples of 30, then I would actually get something that's better than our 6k plus or minus 1. Now, the only unfortunate thing with that is that this 6k plus or minus 1 is really easy to deal with. You know, look at multiples of 6 and the numbers that are 1 and above and 1 below. Here, we'd have a whole bunch of things that I'd have to say, oh, multiples of 30 plus or minus this, plus or minus this, plus or minus this, and so on down the line. So these give us a nice rule and a nice reduction that we can deal with. But there's all kinds of other ones that you could do, and you could sort of incorporate whichever primes you want, and you could play around with that yourself to see what sort of categories our primes will run into. I hope you enjoyed this episode of Math Shorts and our look at a property of primes. Primes give us lots of interesting things to play around with. Come back next month for our next episode. Until then, keep thinking.